Section 2, we're going to get into just the gas laws themselves now here. There's several of them that are named after people. You do need to know them. I'll go through a mnemonic later on once we get through all of them of a way that can help you remember whose law is whom's. But all the gas laws relate those different properties that we had. We had pressure and volume. We also had temperature and amount, which was in moles. And those different values that we can measure for a gas are what we're going to be relating to one another. And each law uses a pair of those measurements and just relates those two things. The first one we're going to do here is pressure and volume, and that is Boyle's law. Boyle's law says that when temperature is constant, and this is the big thing, we're going to, constant simply means not changed. And we're going to see this for all the gas laws that we're going to keep one, and technically speaking here, we're also keeping amount. So temperature and amount are constant. Then the pressure and volume are inversely related. Well, what does that mean? Well, inverse, you may recall from previously, as one goes up, the other goes down. So as pressure goes up, the volume goes down. And they illustrate this with a piston. And to be honest, that's how I recommend thinking about it, is imagine a piston, a cylinder of gas. It's sealed here on the end, so I can't get gas in or out. But if I increase the pressure, if I push more on the gas, it shrinks. Big surprise. And if I stop pushing on the gas, you'll notice it wants to reset. If I pull here on the gas, I decrease the pressure on it, then the volume goes up and it wants to slide back down there. And so the two of them are inversely related. As one goes up, pressure goes up, volume goes down, and as pressure goes down, volume goes up. Those two are inversely related. They are opposite of one another. Mathematically, that gives us a formula that looks like this, that the pressure, rather than 1 and 2, although that is usually how I'll label it, I tend to think of it as before and after. Then as conditions change, we can actually calculate what is going to change about the gas. This slide just repeats that, so I'm going to move on from here. You can certainly take a look at it and prove it to yourself mathematically if you want. Boyle's law is related to breathing. There is a model I made of a lung a long while ago, and I don't have it anymore, but you can actually have a straw represent the mouth here and a balloon represent the lung. And then if you put it into a cup and have another balloon over the end of the cup to be the diaphragm, when you pull the diaphragm, it's actually what causes the balloon inside, the lung inside, to inflate and contract. And so it is actually that and not the lung themselves, but instead the diaphragm underneath that's controlling those volume changes, which change the pressure, which then changes whether the air is coming in or out. We're going to do some calculations here with Boyle's law. I will say that later on we're going to get a relationship that has all of these properties, the pressure, the volume, and the temperature, all related to one another. And you're going to get something called the combined gas law. Personally, I always use the combined gas law when I'm solving problems like this. I don't worry about which formula goes with which gas law. I just use this one all the time. And then what happens is if we have a constant temperature and number of moles, if we have a constant temperature, well, then that means the temperature stays the same. If the temperature stays the same, then it's the same as me being able to just ignore it when I do the calculation. If you're not comfortable with that, if you're like, wait a second, I had the temperatures in that formula and I need to use a temperature, then use the temperature. If the temperature's not given in the problem, make up a temperature. If you use it on the same number on both sides of the equation, mathematically it's going to cancel out and it'll work out the same. But the way I do it is I always use the combined gas law formula, and then I just, if something's constant, I drop it out of the formula. More on that later on. But we're going to have here a new volume is what we want to figure out. So volume after equals question mark of a 8 liter. That is a volume before sample that is initially at this one here. That is a pressure before, or an initial pressure, and this is a pressure after. Well, real quick, just doing a quick check here. The pressure has definitely gone up, and if the pressure has gone up, then I'm going to expect my answer for the volume to have gone down. It's a quick way to check yourself on doing these. So we have pressure before times volume before is equal to pressure after times volume after. And so then The pressure was 550 millimeters of mercury times by the volume was 8 liters is equal to 2,200 millimeters of mercury times by the volume after. To get the volume after alone, we have to divide both sides by 2,200 millimeters of mercury. And then the millimeters of mercury cancel out on both sides, and we're left with liters for a unit. That's another quick way to check your answer is, does it make sense for a volume to be in liters? And yes, it does. At this point, though, we're just ready to punch that into a calculator. 550 times 8 divided by 2,200 gives us a volume after of 2.0 liters. And again, as I mentioned, before, after works, 1 and 2 work the way that your textbook has it. Initial and final, I've seen those used as well. It doesn't really matter as long as you can keep the two pressures, the two volumes apart from one another. This one here, we're given multiple choice, but it's the same basic problem. Sample of oxygen gas has a volume of that and a pressure of that. I know that this is a pressure, even though it doesn't say specifically that it's a pressure because of the units. What is the new pressure? So pressure after equals question mark when the volume changes to this volume after. Well, the volume is bigger afterwards, and so then that means I expect the pressure to have gone down. Let's see, is that enough to answer this one? No, we can say that it's not that one for sure, but we can at least eliminate the one answer. And so once again, we have pressure before times volume before is equal to pressure after times volume after, and that is going to be 600 millimeters of mercury multiplied by 12 liters is equal to pressure after is what we're solving for this time times 36 liters. Divide both sides by 36 liters. Our liters units cancel out, and so we'll be left with millimeters of mercury, which makes sense. Punch that into a calculator, and we get A is equal to 200 millimeters of mercury. Since they have questions numbered here and down here they have containers labeled A and B, I'm going to use volume initial here like they have there. And then these two here are volume finals. And so looking at these two here, if our helium gas is in here, then here the final volume has gone down and here the final volume has gone up. The questions are which one of these occur within each case. And so we have, if we decrease the pressure, then we expect the volume to go up, and the volume going up is choice B. And then this one here is going to be the opposite, because if we increase the pressure, then we're going to decrease the volume, and that's going to be choice A. Going back to doing it mathematically again here, pressure initial times volume initial is equal to pressure final times volume final. The initial pressure is 850 millimeters of mercury. The initial volume is 120 milliliters this time rather than liters. Not a big deal. Mathematically, it works out the same as long as your units are the same on both sides. 425 millimeters of mercury, and we're solving for volume final. I'm going to skip the algebra step there, and I hope you can work that out, and certainly it's worth practicing for you, but our final answer there is C, 240 milliliters. Our next one here, we've got something similar. We're told the volume of this one is 6.4 liters. That's a really big balloon. We're talking a balloon that is 3 2-liter pop bottles big. That's a huge balloon. At a pressure of 0.7 atmospheres. And then if we increase the pressure, so the pressure here from here to here, the pressure has gone up, then what happens to the volume? Well, then the volume is going to go down, and if the volume is going to go down, that's going to be choice A there. The smallest balloon, this one here, would be the same, and obviously this one here would be a volume going up balloon. That finishes up section 2, Boyle's Law.